Okay. We are doing L'Hopital here. This is a rule that L'Hopital's rule. Recall the limits. The limits that we ended up having 0 over 0, 0 over 0 indeterminate form. Yeah. For example, we had limit of x squared minus 3x plus 2, x squared minus 1, as x goes to 1. Yeah? What did we do to evaluate that limit, to be able to evaluate that limit? You remember it? Huh? Yeah? Factor it, cancel it, yes? The game was that what causes the numerator to be 0 is the factor x minus a. And you will see 1 in the denominator, x minus a. So you can factor that x minus a. So factor, then cancel was our strategy. Now, I want to do a little bit different game here. And as a result, you will see that this method of factor and cancel, or factor then cancel, the vanishing factor, can be packaged nicely in what is called L'Hopital rule. Okay? Let me show you here. So before we would say, okay, let's factor x minus 1 from the numerator, x minus 1 from the denominator, cancel it, and evaluate the new one. Instead of that, I want to rewrite this as a different limit. First thing, let's say this guy is f, and this guy is g. Okay? Oh, why did I write limit up there? My limit is still here. I say that, look, f at 1 is equal to, f at 1 is equal to 0, yes? So I can, in the numerator I had f of x. Now I can say minus f at 1. Why I'm doing that? Just be patient, and you will see why I'm doing that. But the key point for me is that by subtracting numerator, f at 1 from the numerator, I'm not changing anything, because f at 1 is 0. I do the same thing with the denominator. Again, the denominator, when you plug it in, you get 0. Plug 1 into your denominator, you get 0. So that's g at 1 is 0. So I didn't change anything. And then I come and multiply or divide both numerator and denominator by x minus 1. Two things should come to your mind. Well, didn't you change the function by doing that? Did I change the whole function that I'm trying to find the limit for? No, because I divided both numerator and denominator by x minus 1. The second question is that why you're doing all these work? I'm hoping that you kind of see what is happening. What you see in the numerator, does that remind you anything specific? What do you see in the numerator? Yes, please?
It's like the definition of derivative.
This is definition of the derivative for f at 1. And this is the definition of the derivative for g at 1. In other words, if I'm sure that this limit is not 0, I can apply quotient law and turn this limit into limit of the numerator and then limit of the denominator. Yeah? And we know that both numerator and the denominator is equal to, they are differentiable, and both of these guys will give you derivative of the numerator, derivative of the denominator. Let me rewrite the left-hand side another time. Sorry, I am not doing very well here. Okay. I claim that by doing that work, I kind of got rid of the vanishing factor. Why? Let's differentiate the numerator. The numerator is 2x minus 3, and differentiate the denominator. If we set x equal to 1, x equal to 1, now this is something that we can evaluate. If it is 0 over 0 for general function, you can repeat this process. But forget the middle steps, and you see that it says if your limit is 0 over 0, the limit can be evaluated as f prime at the numerator over g prime at the numerator. And before I write the more elaborate version of that, I want you to see this, that instead of doing factor and cancel, which is only possible for limited type of functions, now I will do something which goes along those lines and call L'Hopital's rule. So I am replacing that strategy by that. What is L'Hopital's rule? It says let f and g be differentiable functions. It's enough to be differentiable around a, and limit of f of x as x approaches to a is 0, and it is equal to limit of g of x as x approaches to 0. So I have two differentiable functions, and limit of both of them as x approaches to a, both of them a, is 0. Then you can replace limit of f of x over gx, which is obviously, based on the result given there, is going to be a 0 over 0 case. You can replace it with, here I said that you can replace it with f prime at 1 over g prime at 1. But this is a weak version of L'Hopital's rule. What you can do is that you can replace that limit with completely new limit where the numerator is replaced by f prime and denominator is replaced by g prime. And seeing what is happening here, we are getting rid of the factor x minus 1, kind of is the idea. So replacing f by f prime and g by g prime works almost the same way as this one, with one big difference. I am not going to be involved in factoring at all. I just need to do differentiate numerator, differentiate the denominator, and everything will go on smoothly. Does that make sense? Does it? Yeah? Okay. Let's see some example or examples. Find limit of cosine x minus 1 over x squared as x goes to 0. And let me erase this one. I don't need this anymore. And limit of e to the power x minus 1 over tan x as x again goes to 0. Let's see what we are trying to do here. Now, I'll do this one myself, and then I'll give you the other one time to do the other one. Okay, I have a limit of quotient, so I'll start checking the limit of the denominator. This is polynomial, that's just substitution. It will be 0 squared 0. Cosine 0 minus 1 is 0. So I am in the indeterminate form 0 over 0. L'Hopital rule say that whenever you have 0 over 0 and your functions are differentiable, go ahead, apply L'Hopital, replace numerator by the derivative of the numerator, replace the denominator by the derivative of the denominator. And keep this in mind, that differentiating numerator, replacing numerator by the derivative and replacing denominator by the derivative is doing this thing, factor cancel in a fancy way. We love it, yes? Without doing all the factoring and making all those mistakes, I can go ahead and do this one now. L'Hopital rule says that this limit is equal to this limit here. It has nothing else to add to that. Now, I turned my old original limit into another limit. Forget where this is coming from. This is limit of a function divided by another one. We repeat all the steps we do always when see such limits. Find the limit of the denominator, 0. Limit of the numerator, 0. Okay, forget that this is a result of L'Hopital rule already applied one time. I have this limit, again 0 over 0. I can differentiate numerator, I can differentiate denominator. Why can't I apply another time L'Hopital? Sure I can. That's the power of L'Hopital, yes? It says whenever you see 0 over 0 and both numerator and denominator are differentiable around that point, do replace them by their derivative. Replace numerator by the derivative of numerator. Replace the denominator by the derivative of the denominator. Now, well, I can simplify this and I can write, okay, there is a negative half times limit of cosine x as x goes to 0, but that is nothing but cosine of 0 times negative half, and that gives me negative half times 1. Yeah. You are now given a very strong tool, which is doing a very good job in resolving 0 over 0 indeterminate cases. The only condition that you have to check, obviously, is it 0 over 0 not? The second thing is the numerator differentiable? Is the denominator differentiable? Yes, I take that.
For the sine one, could you not just use sine x over x as limit approaches?
That's right. You can go ahead and use the fact that we had before, that sine x over x as x goes to 0 has limit 1. But I just wanted to show you now all those works that we have done together using sine x over x limit goes to 0 is equal to 1 and factor and cancel. All these things now unified in one strong tool, L'Hopital's rule. But you're very welcome to cut that chain anywhere and use the previous facts that you know. Any other questions? Any other comments? How about you start working on that one? I'll give you 1 minute. Don't rush. L'Hopital is a very strong tool, but you have to make sure that the assumptions are there before you starting using it. You have 30 seconds left. We see limit of quotient. The first thing is that see what is or what are the limits of the numerator and denominator separately. Here we find that limit of the denominator is 0, limit of the numerator is 0. Both of them are differentiable. That means I can go ahead and use L'Hopital. And it means that replace numerator by its derivative, which is just e to the power x. Replace the denominator by its derivative. In this case, it's secant squared x, as x goes to 0. Yeah? I have completely new limit. Now I want to evaluate that limit. Limit of quotients of two functions. First thing, check the limit of the denominator. Limit of secant squared as x goes to 0 is 1. So that means that I can apply quotient law, and I get limit of e to the power x as x goes to 0, limit of secant squared x as x goes to 0. This is continuity. It tells me you just plug in. These are good functions. And that is equal to 1. 1 over 1. Any questions, any comments there for me? Let's do one iClicker question. Can anyone please check and confirm that you can see what's going on? I'll write it down up there, actually.
Anything? There's nothing.
Okay. Go. You cannot see it? I didn't. Oh my God. This is. Again, I started the other class.
Why would you write arc sine instead of just sine inverse?
Both of them are the same thing, different ways of writing. Can you see it now? Okay? Go ahead, please. 90 seconds should be more than enough for this to be completed. And as someone already asked, arc sine is the same thing as sine inverse. First thing you have to check, this is important, this is part of the game. If it is not 0 over 0, you're not allowed to use L'Hopital, okay? Here you get 0 over 0, and then you say, okay, I have derivative of the denominator, replacing the denominator, derivative of the numerator, derivative of arc sine or sine inverse. Maybe I should write it somewhere here to recall that dx of sine inverse u is u prime root 1 minus u squared. In this case, u is x squared, so u prime is 2x. 1 minus x squared is squared x to the power 4. Okay? And then you see that this is, let me simplify first. We can write it this way, yes? Now, you can write it as one function, 2x, over another function, which is sine x times root of 1 minus x to the power 4, yes? But note that if I multiply these two, I will have longer and more complicated derivative. If I consider this part separately, however, it will be limit of this guy is 1 over root 1 minus 0, which is just 1. So I can first use product law and separate these two limits just to have a simpler limits to deal with. And then the limit of first part is 1 times limit of the second part. Now I have another limit that I need to evaluate. And I see that this is another 0 over 0. I can use L'Hopital. I report that I see it is 0 over 0. It's very important. I see it is 0 over 0. Now I'm allowed to use L'Hopital and get this thing to 2 over cosine x as x goes to 0. And that is quotient law 2 over cosine 0. That's 2 over 1, and that is 2. I'm closing the iClicker question. Please put in your answers so that the attendance is taken. Okay, I'm closing. 5, 4, 3, 2, and 1. Okay. So that was our clicker today. Now, the next thing I want you to know is that this is a remark. Which says, I can do the same story not only for the full limits, but also for one-sided limits, and also for limit at infinity. So L'Hopital's rule works for limit as x goes to one-sided functions. And when it is one-sided function, your function is differentiable. There's no problem. But if your function is only defined on one side of that point, you just need to make sure that one-sided limit of derivative exists. That's what it means, as well as limit as x goes to plus or minus infinity. The assumptions are the same thing. Still, we are going to have 0 over 0, but instead of x approaching to a number, I may have x approaching to one number from one side, or x approaching to the number x going to plus or minus infinity. This one is not very complicated to understand. This one can be understood through you remember limit at infinity, we can replace it by limit as x goes to 0 kind of thing. You write it f of 1 over x rather than f of x. So that could be understood through that trick that, okay, these are different versions of L'Hopital for more general types of limits. And let's do some examples for that. Again, the condition 0 over 0 differentiability is all there, but we are trying to do it for more general functions. Okay, I'll give you 2 minutes at least to start one of the examples. You should be able to finish one of them at least, but I'm hoping that you will go at least 1.5. Go ahead, 2 minutes is there for you to complete that. 1 minute left. Okay. It is one-sided. We have no issue with differentiability of the numerator and the denominator. And we have 0 over 0k. So based on the remark there, we can apply L'Hopital's rule, which says replace the numerator by secant square minus 1 and the denominator by as x goes to 0 from the right, yes? Then you do forget where this is coming from. This is another limit, quotient of two nice functions. We try to find the limit of the numerator, denominator, you get 0. The numerator gives you 0. It is 0 over 0 indeterminate form. And then we have L'Hopital's rule, which is replace the numerator another time. L'Hopital doesn't see where this is coming from. It's just about this one. Replace the numerator of this guy by the derivative of secant square minus 1. U to the power 2, the derivative is 2, u prime. Derivative of secant is secant times tan times u to the power 1, which is another secant. We had a secant in the derivative, so I can write like that. In the denominator, we get 6x plus 12x squared. And then we have another time 0 over 0. Limit of the denominator is 0, limit of the numerator is 0. Then we try to find the limit, replace the limit by a new limit, which L'Hopital tells us how to do it. And this is product rule, derivative of the denominator. It will be 4 secant squared x tan x, derivative of first one times second one, this will be squared, plus first one itself times the derivative of the second one. This is secant squared. Derivative of second one is another secant squared. We multiply, get secant to the power 4 over 6 plus 24x as x goes to 0 plus. Now, this time, when I find the limit of the denominator, I get non-zero value. That means you have to stop. You cannot go further using L'Hopital. I have to use other laws here, other rules, other tools. And in this case, we have quotient law, which gives us, okay, limit of numerator. This part is 0, plus this part is 1. This part is 6 plus 0. And that is 1. Is it 1 over 3? Am I doing it right? Hopefully. I could easily make some silly mistakes there. Any questions? Any comments? We are all happy? Yeah? Okay. Then let's do this other one. It is as x goes to negative infinity, remember. Whoops. E to the power x, as x goes to negative infinity, goes to 0. So I have 0 in the numerator. Here I have 1 plus 0, ln of 1. So ln of 1 and 0 in the numerator. That's again 0 over 0. It is 0 over 0. I claim that I can use L'Hopital. The only things you should worry about is that, wait a minute, this is not x going to a number, it's going to infinity. But our remark, or thank you to the mathematicians who have worked all the details of these things, and now we know that for limit at infinity also this works. In other words, my tool is stronger than its original or the first version that I wrote on that board. And that is limit of e to the power x over ln of u is u prime over u. Let's for a second simplify that. Why I'm simplifying this way? Because I want to write it in a quotient of two function forms, and then go ahead from there. And in this case, it seems that now in the right place. But if you see anything that simplifies your limit, this could be algebraic simplification, separating a part. You remember on this example, we separated limit of 1 over root 1 minus x to the power 4 because we knew that it's not going to play an important role. So we could separate that part. If you see anything like that, do it so that even if you're using L'Hopital, it will be easier to differentiate. In this specific example, if you don't simplify, you have to run this. Well, L'Hopital won't get you anywhere. You will get infinity over infinity again, infinity over infinity again, infinity over infinity again. It won't be able to resolve it. But if you simplify and write it in the new form, this is just simple limit values, limit laws, basically. Any questions? Any comments for me? Okay. Now, we had L'Hopital resolving. L'Hopital was resolving 0 over 0 cases. Bless you. It can also handle the other indeterminate form that we studied before. Do you remember what was the other indeterminate form? Do you remember that? Infinity over infinity, yes? Infinity over infinity, in that case, instead of factor and cancel, we factored out the dominant term and then canceled. Now, L'Hopital version for infinity over infinity. So I'm writing a bit loose version of L'Hopital's rule in this case. Let f and g be differentiable functions around point A. So not at A, but around A, it's working nice. It's differentiable. And you know that limit of the numerator as x goes to A is either plus or minus infinity. And you know that the limit of gx as x goes to A is plus or minus infinity. Then you have L'Hopital's rule again, which says limit of f of x over gx is equal to limit of f prime x over g prime x as x goes to A, as x goes to A. F prime over g prime. I don't know why I did write it there, but it is now working that way. So not only it handles 0 over 0 cases, but also handles infinity over infinity cases, could be any form. And in this case, let me do some examples. Limit of ln x over cosecant x as x goes to 0 plus. Ln is only defined on 0 plus. And also, it will work on limit at infinity as well. So in this case, you get limit of e to the power x plus 3x over x squared plus 2x plus 10 as x goes to minus infinity or plus infinity. The first thing to see, we are almost out of time. Let me at least finish one of these ones. So ln x, remember the graph of ln x? As we go to 0 from the right, it goes to negative infinity. So I have negative infinity here. Cosecant is 1 over sine. As x goes to 0, sine x goes to 0. So 1 over sine is going to be infinity. And in this case, it's going to be plus infinity because we are approaching to 0 from the right. So then I can take L'Hopital here, and I get 1 over x minus cosecant x cotan x. That's the derivative of cosecant. Let's simplify this guy here. Minus cosecant is 1 over sine x. Cotan is cosine x over sine x. So my limit, I can rewrite that, is 1 over x over minus cosine x over sine squared, yes? But I can simplify this way. This will be minus x cosine x sine squared x as x goes to 0 from the right. Yeah. And then you see it is 0 over 0. This is again 0 over 0. I can apply L'Hopital. Well, actually, before it was infinity over infinity. Now it turned to 0 over 0. Well, even better. And I know that L'Hopital works here, and we have 2 sine x cosine x over minus cosine x. Okay, derivative of cosine x is negative sine x. There's a negative sign here. This will be as x goes to 0 from plus. Now, limit of the denominator, this part is 0, this part is negative 1. So I can use quotient law, evaluate that, and I get minus 1 plus 0. In the numerator, I get 0. The value is 0. L'Hopital now not only helps us to find resolve 0 over 0 indeterminate form, but also helps us to do infinity over infinity. And on Monday, when you come back, we will have a bit of more work. Now I want to introduce you to new indeterminate forms, and you will see that those indeterminate forms can always be turned in either 0 over 0 or infinity over infinity, and hence we can use L'Hopital to evaluate those ones. Have a great day, good weekend, and see you all on Monday.